Hi, my name is Ivan Bugoma. I'm a junior at Georgia Tech in the mechanical engineering field, and today we are going. The purpose of the post-quiz tutorial is to go through the problem and the main concepts that we need to use to resolve the problem. The problem states a thin-walled hollow circular tube and open at both ends that is represented by this drawing here. So we are to calculate the electric field caused by this tube at this location here. In order to do that, we need to focus on first three main concepts. The first concept is we need to find the distribution of the charges over the tube. Here we assume that the charges are evenly distributed through the tube, so we can find for any portion of this tube we can find the charge. So the second concept will be to design a road we will go through in order to actually calculate the electric field made by the tube, and this road will be by calculating the electric field made by rings that go from the origin and the end of this tube. So we want to assume that this tube is made from of an infinite number of rings of thickness dx that go from the origin 0 to the end here, and we want to calculate the electric field of all those rings at this location here. And this is the way we should go about this problem, because we can't just calculate the electric field of this tube here. The formula doesn't exist. However, the formula for the ring exists. So by integrating the tube over its length and over any amount of ring with thickness dx, we can calculate basically the addition of all the rings of the electric field of all the rings at this location here. The third concept we need to use here is a very important one. In order to be able to set up the integral, we need to be able to find what will be the variables that will change during the change of the integral. And here we basically use distance. For any ring on this tube, the distance between the ring and the point here will differ. It will always change because of the ring. The location of the point on the x-axis will not. So what we should do for the distance is the simple formula that we were given, that the distance is equal to the observation location minus the source of the electric field. And this is at the bottom right here. We have that z is equal to w minus x. W is the location of the observation and on the x-axis, which is w, and x will be the location of any ring on this tube. So x will go from 0 to L, and w will always be w. It will the location of the observation. So the first concept was to find the distribution of the charges. The distribution of the charges here, we named it q prime, and q prime is going to be equal to q over L. So that means that for any position on the tube, we can find the amount of charge that is at this position. Second, we need to find the amount of charge that will be on any ring on this tube. And to find that, we just multiplied, we just call it dq, and dq is going to be equal to q prime multiplied by dx. dx here is the thickness, which makes sense. So the amount of charge on a ring will be equal to the charge per unit length multiplied by the thickness of a ring, which is totally fine. The first concept is already in our pocket. Before going to the second concept, which is to be able to find the distance between the location and the tube, we need to use the electric field of the ring, the formula of the electric field of the ring, in order to find the electric field of any ring at the location. This formula is given, and it's here. It's E ring. E ring is equal to 1 over 4 pi epsilon 0 dq multiplied by z, the distance, divided by r squared plus z squared, and everything at the power 3 halves. This is the formula for the ring. This is the formula we need to use to calculate the electric field of any ring here on this length L. Given that, in order then to find the electric field of the whole tube, that means all the rings that are possible to fit here with thickness dx, we just need to find by polishing the electric field of the ring that we have here, we can see that at the end we get that E ring is equal to 1 over 4 pi epsilon 0 Q over L, because Q over L is found here. So from the dq times z that we get here, we get Q over L times z divided by r squared plus z squared to the power 3 halves multiplied by dx. This is the formula we need to use in order to proceed to our next step. The second concept that we needed to use was to actually find the distance. And the distance will be used with the integration of the electric field of the ring. The distance that we said we will use was z, that we put here. Z, if we do observation location minus source, z is equal to w minus x, which is exactly what we want. We see here that electric field is equal to this formula times dx. dx is going to be the variable of integration, and here we see that our z changes with x. Hence, to find the electric field of the tube, we need to integrate the electric field of the rings over x, and x will go from 0 to L. Then we proceeded to the next step of our problem. The next step of our problem is just the electric field of the tube is in the integration of dE ring from 0 to L. The only variables that will change through the integration are the variables that contain x. The only variable that contained x that we saw was the expression where the distances was replaced by w minus x. Hence, here in our formula, we see that E tube becomes 1 over 4 pi epsilon 0 Q over L integral of 0 from 0 to L of w minus x over r squared plus w plus x, everything squared, and the denominator raised to the power of 3 halves dx. Having that, from here, the only note that you have to take is the main step from here is to actually find the integration value of this one, and this can be found at in an integration table that you can find in the book or in the also online. So here you can see that the integration of, this is the formula, you can see that the integration of a minus x divided by b squared plus a minus x squared to the raised to the power of 3 halves is equal to 1 over b squared plus a minus x everything squared, the denominator to the power of 1 half. This is the formula needed to use in order to continue the integration of the formula. So from here, using the formula we just saw, we end up here. So plugging in the values from 0 to L, we just end up with the result here being the electric field of the tube at the position we were asked to calculate. And this electric field is equal to 1 over 4 pi epsilon 0 q over L, everything multiplied by 1 over r squared plus w minus r squared plus w minus L, everything squared, and the denominator raised to the 1/2 minus 1 over r squared plus w squared, the denominator raised to the power of 1/2. Thank you for watching. I hope this video was instructive and was able to enlighten many of the dark areas you had going through this problem. Have a good day.